Okay, guys, as promised, this is the Kale screen. And we are going to do everything we've done theoretically previously. We are going to be doing on the Kale. So it's quite simple, guys. I've got my card connected to my desktop. It's on. I've got the switch on, so I can see the LED. And what else is I've got a project, and I've got all my configurations set. What kind of configurations? You remember there are some project configurations that you have to do in your Kale project properties, which you can find in your lab menu. And I'm sure in your labs, in your demonstration lab this week, your teaching assistant has provided this information to you. So you've got a sample project. You can do this. You can do anything you can just see on the screen right now. So I'm going to be doing it the way I do it, just like a theoretical example. But this time, I have every Kale screen and everything is here. So I've got this simple code. Can everybody see the code? I'm just trying to make it big. So these are the codes. This is my first line. So I've got an instruction memory. This is my first line. So line 38, we said, corresponds to an instruction memory, we said. Which instruction memory will be able to see it? How? For example, I'm going to start the code, put a debug line here. It's going to stop there, and I'm going to check the PC value, which will show me the exact value of the address memory. Okay, let's do it. Guys, what you do is you first save your code. Then you build your code. What is the build? Sorry, where's the build? Actually, ben debug ekranındaymışım ya. Okay, so you have your code. You first save your code. Then you build your code, rebuild your code, so that when you rebuild your code, what happens is you've got these lines of code. It is converted to machine code. Now it's ready to be loaded into the card, but it's not loaded yet. There is another button for it, which is this load, it says. Now it's successfully downloaded to the flash memory of my card. Okay. Recording, right? Okay. So I've got everything ready. What I'm going to do is I'm going to debugging my code. Debugging means I'm not going to let the clock run. I'm going to just say the clock, okay, get to the next program counter. I'll be telling it, because debugging is actually freezing the program counter so that you can make analysis on your program. So where to stop? This is my first line of code, right? I'm just clicking here. I see a red circle button, which means when the code starts to run, it will stop there and wait for my instructions to continue. So how do I do it? I use this magnifier glass icon with a D inside it, which stands for debug. I'll start the debug session. And it asks me, I'm going to have a limiting of 30K because you haven't bought the program. You are poor people. We haven't bought it, but we don't need to because our programs are much smaller than 32K. But if you're going to do some professional stuff, go buy it. Okay, very good. Now, it hasn't started yet. The program counter is set and ready to go. It is waiting for my instructions. I'm going to be clicking run, which means start. And when it's run, it's going to run or stop at my first breakpoint, which is here. It's the first line of code. So when I push here, you can press F5 as well. I click here and it stops here. Be careful, guys. If you have this yellow triangle here, it means it has not yet executed this line. It will execute it, but not yet executed. So if you have a yellow line, it is not executed yet. What is it going to do? It is going to put this large 32-bit number to R0, right? And this is an LDR operation. LDR operation was 32 bits. You remember 32 bits? So this is a 32-bit number. So the entire number will be transferred to R0. Is it really? Well, I've got the values, the live values of R0 and R1. If I just take one step forward, I can see it. How to take one step forward? You can do it many ways. You can put another breakpoint here and say jump. Or there is this F10. It means step over, get to the next line. F10 in almost all programming interfaces like this for any language Python C, it means the next line. So if I press F10, and it's at the next line. So which means this instruction is not finished yet. It's not started yet, but this one is finished. What did it do? It got this value and put it at R0. Yes, it did. Yeah, it is here, as I can see it. It successfully did it. This is how we debug, okay? And this is how you're going to do debug on your codes as well. So you're not sure about a code, specific code you've written on your exercises. You want to test it. This is how you test it. Okay, this is the way you debug. Okay, you've got it here. And the next line, I press another F10. It moves, and did it put this 2 value in R1? Yes. In R1, I've got this value. And the next line is R1 plus R0 written to R0. Okay. Do I know these numbers as signed or unsigned? I don't know. I just do the summation. I just write the binary numbers here, do the summation. Let me do that for you, guys. Let me do that for you. I'm going to be writing the binary version. So F is 111. 1111, 1111, 1111, 1111, 1111, 111. Sorry. So I've got 8, 1, 2, 3, 4, 5, 6th F, 7th F, and the last one is an E. Okay, this is the number. So then the other number is 0, 0, 0. So let me just move just behind so we won't be confused. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Just let me this longer. So 0, 0, 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, because it's 2. You do a summation. 0 plus 0 is 0. 1 plus 1 is 1, 0. So let me write it. Let me write it with my pen so it will be more easy to understand. 0 plus 0 is 0. 1 plus 1 is 1, 0. So I put the smaller digit and I've got a carry here. 1 plus 1, 0. The carry moves, so 0 all the way. So it is all zeros with a carry, guys. As you can see, the sum is 0. So what I do is I check the operation and just stop annotating. I check the operation by pressing F10. Yes, in R0, I have zeros. Do I have the carry? Do I have the Z bit? Well, you have the program status register here. What you can see, Z is bit 1, carry is 1. This is how you control your things and your flags and blah, blah. This was a demonstration of the theoretical stuff that we have gone through previously on debugging version of Kale. Any questions about the first part? Because in the next part, I'll be jumping to functions. I won't be able to return to this part. Could everybody follow what I exactly did?
Evet
Okay.
hocam.
Thank you. Very kind. Okay, annotate, clear all my drawings. Okay, guys, now this was...
Hocam benim bir sorum olacak bu.
Please.
Az önce yazdığınız çok devasa bitlik bir sayıydı. Bunu nasıl kaydetti ki?
It was 32 bits.
32 muydu?
Exactly. You've got 8 nibbles. Each nibble, this is 4.
Her biri
8
4
times 4.
tane.
Yeah. So,
Peki bunu memoriye kaydetti değil mi?
Registers.
Register'lar çünkü 16. Register'lar 16 bitlik değil mi?
No, in our mic, very careful guys. All registers are 32 bits in our system. Everything is 32 bits. We are a 32 bit system. Careful. Okay?
Evet, register'larda F yazabiliyorduk register'larda, doğru.
Exactly, 32 bits. So,
peki bu binary yazdığımız numara nereye kaydoldu? Binary hali.
Actually, it is in binary here. That's how you show it. Everything is binary.
Register'lar binary değil ama.
Actually, everything is binary in a microprocessor. That's how we represent it here.
Ha, gösterim sadece
öyle. Exactly.
Daha kolay
Everything is binary.
gösterilsin diye. 32 tane yazmayalım diye.
Exactly. So that you understand it very easily.
Anladım.
Okay? Everything is binary. There are no non-binary computers. There are quantum computers that we do not exactly know how to use yet. But every microprocessor in the entire planet, we have billions of them, they are binary. Okay? But binary is a bit hard to handle. That's why we use nibbles, 4 bits, and hexadecimal digits, so that we could do the operations more easily. Okay? And remember, guys, about this operation, in 2's complement, this number is actually -2. So the operation was actually -2 plus 2, which is 0. That's why the answer was 0. Okay, so you get a sense of the arithmetic operation as well. Good. Now we're at the second part of the code. We move 5 to R1, and it's called self-sum. We are jump. This is BL. So this must be a function. So I've got this function here, right? So let me get down. So this is function self-sum. Oh, first self-summation code. The first one is the first self-summation code. This code will sum all values up to 5 because we have 5 in R0. Yes, we have 5. If it was 6, it would have summed them up to 6. It will write the result in R1. So it will be 1, 2, 2 plus, it will be 15. Okay. So how does it do it? We're going to see how does it do it. Let's first jump to that part. So you are here. This is yellow, which means the current line of execution. I'm pressing F10. Now, guys, I have 5 in R0 because I've done it. And I'm going to be jumping to self-sum. Be careful, guys. What we said was about BL, it does 2 things. It changes the program counter and saves the next value of the program counter to LR. Does it really do it? Let's check. So I've got all the values here. So this is LR, guys. Wow, this is LR. And I have some rubbish in LR. I don't care. Somebody put it LR because it was the initial code. So the value inside LR for now is not important to me. And what is the value of the program counter? This is the value of the program counter. Well, this is the exact instruction memory location. So guys, if we are at line 43, line 43 must correspond to the instruction memory address, which is hexadecimal this value. Okay, remember the example that I shown you on the slides. I said that some lines of code must correspond to some instruction memory addresses that we don't know. Well, this interface shows us. So line 43 actually corresponds to this line. Good. So when I do this, when I just press F10, when this instruction is complete, the next value of PC should be written into LR. And the value of the PC should change to self-sum, whatever it is or wherever it is in the instruction memory. Does it happen? Let's do F10. I'll be careful. If you do F10, it will jump to here. You have to do step in, not step over, which is F11, guys. If you want to go inside a function while debugging, you don't do F10, you do F11. So I do F11 and I come, couldn't do it. It doesn't listen to me. F11. Hello. F11. It did. So guys, it just came inside factorial. Did it happen? So guys, in LR, I have a new value, which is the location of this, in LR, yes. Because it's most probably the next location, which is here. Because let me get back. We are here, guys. We jumped to here. The next line of code that I was going to call was this. And it must be saved in LR. So I've got a value in LR. So LR, this value is most probably this line of code, guys. I don't know yet. I'll learn it when I return. What about PC? PC has this specific value. So I jumped. That's how it happens, guys. So self-sum is basically you get R0 and you just decrease R0 in a loop and accumulate all the results over R1 here. You check if R0 is 0. When R0 is 0, you just jump out. Does it happen like that? Let's see. I'm just going to click F10. Just so in R1, I have 5. I decrease R0 by 1. R0 is 4 now, as you can see. Is R0 0? As I had S here, it's changing the bits. The Z flag is not 0. So it shouldn't jump. So I don't jump. I continue to here. So I continue. I add R1 to R0. 4 plus 5. It is 9, guys. And it makes the summation over and over again, accumulated until R0 becomes 1. And at this point, R0 becomes 1. And I have the summation 15, which is F in hexadecimals in R1. So R0 was 0 at this point. So Z flag became 1. That's why BEQ will jump. I'm jumping with BEQ. It means no operation. Guys, this was a function call. This was a function call. I need to get back. How will I get back? Do you remember? I got back using a specific instruction, which is BXLR. If you don't have it, you won't be able to get back. Proof is here. As you can see, I will not be able to get back. It will continue down here, down in your code. So this code is wrong. We stop it. We stop it. We put a BXLR here and rerun the code. I just save it. I just build it. I load it again because I changed the code. Now I do my test again. Then I will see that it returns back. Okay, so let's do it. So it goes and goes and goes. At this point, I press F11 so that it gets in. So it is summing up 9, C, E, and it is F now. So it is 1. Z flag is 1. It's going to jump to here. BXLR. I'm jumping back. Yes, I jumped back. That's how you do it. That's why you need BXLR and BL, the function jump. Well, that's how you debug it in Kale. Any questions? We are going to do this kind of exercises a lot, guys. From now on, it will be all about Kale, I mean, live coding. Any questions? Good. I guess that was a good example. Okay. Now we get back to our slides. Okay. New concept. Very good. Stack. Guys, stack is related to data structures because it's a type of a data structure. And this will be the first time you'll be doing some complicated stuff on learning complicated stuff on microprocessor assembly language. So it will be like we are a bit speeding up. So from now on, I was taking things slow, but from now on, concepts will be coming more fast and fast. So what I recommend is, for example, do this check yourself and change the code, write this code yourself and change necessary codes. You can find projects in your website, your TA provided them there. So do these tests. Otherwise, the course is getting a bit faster now. Otherwise, you won't be able to cope with it. That's my advice to you. And it will be a good exercise to get prepared for the labs as well and for the exam. If you get prepared for the labs properly, the exams will be very easy for you guys. Okay, so let's get back to the stack. What is a stack? Actually, guys, stack is a general data structure. It is not a concept only for microprocessors. You've got it in C or Python, in every programming language. Its data structure is something, a theoretical definition. You implement it on some language or architecture. So stack, I'm going to teach you the theoretical definition. Then actually we are going to be talking about the implementation of it on the device. So it is a basic implementation. The implementation of stack is also called last in, first out. Guys, data structure means it's a type of concept which is designed to keep data inside it. Okay, multiple data. For example, the register is a type of data, right? It keeps one single cell. That's the simplest type of data structure. Solid, fixed length data cell. That's the simple data structure. Stack is a bit more complicated. It can keep multiple data, and the length of data you can keep can shrink or increase. So it is a variable length data. It's like an array of data, but it's got a certain procedural data acceptance and data deletion procedure. That's why it's called last in, first out. You push and pop data out of the stack. So in this data structure, you have basically 3 operations. You can insert an item to a stack. You have an empty stack. You have nothing in it. You insert something. you delete something out of it, and you can display what's inside, because otherwise you will lose the control of what's inside and what is not. So guys, how does it work? Okay, so guys, imagine you have a stack. First, you don't have anything and you put 1 in it. Then you push another value to it. It is last in, first out. So the most, the last thing you put, you can get first. For example, there's 1 here. You push 2, then your stack is like this now. You put 3, your stack is like this now. You put 4, your stack is like this now. You put 5, your stack is like now. If you push 6, the 6 will be on top. The strange thing about stack is, if you have a stack like this, if you want to get a value from stack, you cannot get these down values. You can only get the one at the top. So if you want to get a value, you can only get 6. So you just don't say stack, hey stack, give me 4. No, it can only give you the topmost element, or the lowmost, how you put it, how you draw it. The latest one, the last one that was inserted. That's why it's called last in, first out. You can only get the the first one you can get out will be the last one you inserted in. That's how you put it. That's why it's called last in, first out. So in abbreviation, LIFO, LIFO, LIFO. So stack is a LIFO data structure. You can only get this one out. Any questions about it? Stack being last in, first out. Did you get the idea?
Hocam bunu şey olarak düşünebilir miyiz? Etrafı kapalı bir dolabın içine eşya koyuyormuş gibi.
Exactly. Stacking means tıkmak in Turkish. Exactly. Stack means you can only...
Hocam nereye tıkıp nereden alıyoruz?
Memory. We are going to see that. Stack is a special place in the memory. Nobody can touch it. Only stack. It's called the stack memory.
Anladım.
Okay. So it's not the registers, it's the memory. Okay. So guys, this is the theoretical definition of stack. It's not related to microprocessors, or it's not related to your architecture. When you say stack in software engineering and programming, that's what you understand, nothing else. Last in, first out data structure. Just like your friend said, stacking things on a wardrobe and just only being able to get the first one out. And I was not surprised that came from a guy, not a girl, because girls do not keep their wardrobe like that, guys. I mean, usually there are girls like that, I'm sure, but I don't keep it that way. Okay, so you always stack things in, right? The one you asked. I mean, I'm talking about the guy who asked the question. Anyways, so stacking microprocessors are implemented by using a stack pointer. So at this point, we got an implementation of stack for the microprocessor. The good news is, you can implement any type of data structure in your memory by writing codes, but it is already implemented within the hardware, guys. So actually, you do have a stack system in your hardware you can readily use. How come? Well, it's being implemented by something called the stack pointer. Do you remember the stack pointer SP from the other slides? Yeah, SP. The stack pointer, yeah, actually, it is showing the last inserted element's address location in the memory. It was a bit quick, but we are going to get there. So it's stack pointer. How come? So guys, actually, you have a part of the memory which is dedicated to the stack. And actually, a pointer is pointing to the topmost element of the stack. So this is the stack, for example. If you push a new value, it will be inserted on top of it, right? Imagine I'm going to push 20. So it will be pushed here. The stack pointer will now stop pointing this and it will be pointing this. So if I push something new, the stack data structure knows that I'll be putting it here to the next location and the stack pointer will point here. And if I take something out, it knows that this value will be taken out because it was the last one, because the stack pointer is pointing to it. So this is how you implement it. You need a pointer, a single pointer, which points to the last element. That's how you do stack pointer, stack implementation in ARM. So all as items are added to the stack, I mean pushed to the stack pointer is moving to the next location. And as items are removed from the stack pointer is pointing to the previous location. So the stack pointer is moving up and down. That's how you do it. It was also another theoretical definition, but we are going to get to do it on slides and on Kale as well. Good. So guys, where is the stack pointer? It's a special function register. And since it's a special function register, we will be able to read the value of the stack while we are going over it, because this is the stack pointer. For example, we are going to push a value to the stack pointer. The value of the stack pointer will change here. And that's how we will observe it. And we'll do it in live codes, don't worry. Okay, let me get back to my slides. That's how we do it. Okay, so actually, if you have a memory space and if you have a dedicated pointer to it, you can implement stack. And it's already implemented in hardware in our microprocessor. Okay, so guys, what are the operations? Actually, since it's already implemented in hardware, we have instructions for it. You have an instruction just like LR, just like LDR, just like STR, just like add, sub. You have assembly instructions. And to insert a variable into the stack, we have this instruction, which is push. Okay? Push means you get a register value and push it into the stack pointer. Be careful, guys. If you want to push a value into the stack memory, this part of the memory will be called the stack memory, because to implement the stack pointer, we need a dedicated place in the memory and we need a pointer, right? So I'm going to be calling that dedicated part of the memory the stack memory from now on. So if I say stack memory, please get that I'm talking about that dedicated part of the memory, which is only used for stack. Okay, so let me get to my slide. So guys, if you want to put a value to the stack memory, if you want to push something to the stack, you can only get it from the registers. So you need to have it in the registers beforehand. And you will use this notation. So push R2 means get the value inside R2 and push it into the stack. And the stack pointer will move to the next location. You can move multiple register values like this. It pushes from right to left. Very careful, guys. If you say R0 on R4, it will first push the rightmost one, R4, then R3, then R1, and R0. Okay? Or you can do this. And be careful. If you use a dash, it is right to left. If you use commas, it is not right to left. From the highest to the lowest register. When commas, it is not right to left. It is highest register, first R2, then R1, finally R0. Be careful with these rules. When to push which one. Did everybody get this? So I'm going to be doing these examples. So any questions? I'm going to be doing an example. No questions? Okay, so let's try.
Hocam benim aslında var. Şimdi
Please.
bir tane value'yu stack pointer'a attığımızda o da direkt memory atıyor değil mi? Yani çünkü sonuçta SP'de bir tane register aslında baktığımızda orada.
Yes, SP is a register which keeps the location of that memory, which is pointing to the last position of the stack. Okay, I'm going to be drawing it, guys. This is the memory. This is the memory, guys. Okay, you have many things in the memory. Some part of the memory is actually the stack pointer. For example, this is the stack pointer. It's the stack pointer. It's the initial place of the stack pointer. It's pointing to here. Okay, and I've got some lines of code. For example, I've got this. Let's draw the registers as well. So I'm going to be putting the registers here. So this is R0, R1, R2, R3. I'm going to be putting decimals here, so don't be fooled. So I'm going to be putting 0, 1. This was 0, right? 2, 3. I've got these values inside. You could have written them using hexadecimals, but for the sake of simplicity, I choose to write it as decimals. Imagine in R0, I have 0. In R1, I have 1. In R2, I have 2. In R3, I have 3, for the sake of simplicity again, so that you don't get confused. And I've got some lines of code. So let me write some lines of code, guys. Okay. Push R0. Then push R2, R1 to R3. Keep it, making this capital R or small caps R doesn't matter. Don't forget this. Push R4, R1, R3. Okay, this is the first line of code. This is the second line of code. This is the third line of code. So what happens, guys? What happens? Let's see. This is the first line of code, and it's going to be writing the value inside R0 to where stack pointer shows. Very simple, right? So I'm going to be writing 0 here. What happens also is stack pointer now starts to point to the next location. So now stack pointer is pointing to here. Everything clear? So the next one is push R1-R3. I'm going to be pushing a number of values to the stack. Which one first? Here's the definition goes. Pushes from right to left. So the rightmost one, then the next one, then the leftmost one. So I push R3 first. So I've got this here. 3. Now, guys, stack pointer is pointing to the next location. Now, then R2. Now, stack pointer is pointing to the next location. Then stack pointer is pointing to the next location. I have done 3 push instructions together. Okay. To here. So, guys, I've got another set of 3 chat. You're asking why push R0, the first line of code, was done the operation in the memory. Please, I couldn't get it because we did. Push R0 is here. We've written it in the memory. Alperen asks. Okay, you got it. Thank you. No worries. No need to be sorry. Okay, guys. So I finished with this instruction as well, and stack pointer is pointing to here, right? So the next one is R4, R1, R3. We didn't put R4 here, so let me put this. Let's say this is R4. And to make this simple example continue, I'll make the value of R4 4. It could have been something different, but I'm not trying to confuse you. I'm trying to make you understand. So, guys, if this is R4, R1, if there are commas, what was the rule? Pushes the highest to lowest. So first the highest register. What does it mean? So R number means the highest. So R4 is the highest, not the value. The index, it's talking when it say highest or lowest, it's talking about the index over the register. So the first 4, then R3, 3. So let me just, so the memory, we are not finished. So where am I? So this is it. Okay, and sorry, and I've got 1 because last one is R1, and this guy is now pointing to here. Okay. Okay, I think it was a very simple example, but it shows how does it work in the memory. Guys, this is memory, not the instruction memory. Be careful. Instruction memory is where the lines of codes are. Memory is where your data is. Okay? It's already, so this push instruction automatically can get things to memory. Previously, I told you if you want to write something to memory, you use str. That was correct. But str cannot write to that dedicated stack location. Only stack operations instructions can write there. Push operation can write there. And actually, pop operation will read it from there. Any questions about this part? Good. No questions then. No questions. Okay, I'm going to be continuing with the next slide because it will show us an operation of the pop. Good, pop. It's the exact opposite. It reads from the memory to the registers, but also it changes the location of the stack pointer. So for example, if you say pop R2, it will get the topmost value of the stack, write it to R2, and get the stack pointer down. If you say pop R0 to R4, it will do a number of multiple pops together, but this time from left to right. First the leftmost one, then the rightmost one. It was not the case for the push. It was the rightmost one first, leftmost one the last. It is the opposite here. There's a reason for that. You'll get it. Don't worry about it right now. And exactly, if you have dash, this is the case. If you have commas, it is the lowest index first, so R0 first, highest index register last. Okay? Actually, I didn't tell you, but you can push LR and pop PC as well. We're going to get there. Don't worry about them. Just consider these are some exceptional cases for some specific purpose. We're not there yet. Let's talk about the registers and understand how the stack pointer works. Okay, don't worry about it. Okay, so this is how you pop. So let's write a simple program. Again, we've got this annotation tool I love. So guys, I'm going to be writing random code. Let's write it. Pop R2, then pop R1 to R4, then pop R0, R3. Not PO, of course, pop. Very good. So guys, imagine when I call these lines of code, imagine this is the exact values of the stack pointer. So it is like I'm running this code just after the line, I ran the previous code with pushes, okay? So this is first the pop one, pop R2, which means, look where stack pointer is pointing. The value before it is where is the last one inserted to the stack. So it will be the first one out. So pop this value and write it to R2. Very good. In R2, I have this value of 1 now. And since there's a push operation, I'll be pointing to here. Now, guys, did I lose this one? I theoretically lost that one. Actually, it's still in the memory. But I'm going to delete this, not to confuse you, okay? But actually, it is still in the memory. But let's do it this way, because it is more easy to understand the stack operations this way. But actually, although I have deleted it, the pop operation does not delete that value from the memory. Whatever, we don't care. Guys, SB, this is the case.
Stack point sadece aşağı iniyor galiba.
Exactly, exactly. Guys, anladığım kadarıyla ben şeyi silmişim ya. Dur bir daha yazalım. R2, so pop R1 to R4. This was, sorry, this was the code, right? Pop R0, comma R3. Okay.
Hocam pop'ta mesela şey yazsanız R0, R3, R2 yazsanız yine push'taki gibi R3, R2, R1 diye mi gidecek yoksa yazdığımız sırayla mı gidecek?
Well, it says if you have commas, it is the first lowest index register. So the order you write is not important in commas. The order of the indexes is important. Indices. Okay? So the order, if you have commas, the order is not important. The first one will be decided by the index value. The lowest index is the first. R0 is the lowest index. R0, that value is the index of the register. The smallest index first, it says, when it's a comma. That's the rule. Got it? Got it? No.
Got it.
I got it. Okay, thank you very much. Guys, we have done this. So this line of code is gone. Now the next line of code, which is this. I have a dash. What was the rule for the dash? For pop, it is the left one first. So R1 is first, guys. So I pop to R1 first because I'll be writing to R1. One is the last value. So this was, guys, did I do something wrong? Biri silmeyi unuttuk değil mi gençler? Evet. Yes. Actually, we have deleted this. O yüzden siliyormuş ya. Okay, this was the case, guys. So I'll be deleting the value inside R1 first, and writing 3. And this one gone. And this, don't do it. Tamam abi yapma, boş ver ya. Okay, so büyük olduğu içinmiş. Okay, how can I do it? Şöyle yapayım arkadaşlar. Okay, so okay. Olmayacak bu. Okay, so stack pointer is not pointing to... dur ya, şunu şöyle yapabilirim. Kafada bas çalışmıyor ki. Okay, so stack pointer is not pointing to here right now. Stack pointer is now pointing to here. So it is. SP is pointing to here. Now R1. It was R1. Then R2. So this value will be written to... Tabii ki bu value'ları kaybettik abi. Onu da bir halt becerecek olsak. This was 3, I guess. This was 1, I guess. Okay. So we got this value. Now 4 to R2. So R2 will be overwritten. Or do I lose this? Okay. Then 1 to R3. And 2 to R4. And stack pointer will be pointing. Okay, we can just to here now, and stack pointer. So, and I have this instruction also gone. That's how you do it, guys. I'm not going to be continuing. So if this is R0, R3, in commas, the lowest register first. So 3 will be written into R0 because R0 has the lower index, and 0 will be written into R3. So guys, this is how you do it. This is the structure. Did everybody get it? How to test this? How to test this? Well, you can use Kale. Let's do it. Let's do it in Kale. So I'm going to clear all my drawings, annotate. And I want you to do it because we don't have much time. I'm going to be stopping here, and I'm going to be giving you this as a homework. I'm not a homework that I'm going to collect, but a homework which you can do it on your own. For example, move R0, the value of 1. So move R1, R2, the value of 5. Push R0. Pop R2. I save it. I stop debugging first. I'm in the debug mode. Save it. I build it. I load it to my card. Flash download failed because I've got an error. What is this? What's the error?
Hocam R2 olmadığı için olabilir mi? R2'a bir değer yazmadık ya.
No, it is not. Because it's going to write over R0. I'm trying to remember the syntax. It's most probably about the syntax. Yes, it's about the syntax. You have to use these parentheses for push because I just forgot it. It's been a year. Okay, guys. So I've got a breakpoint here. I jump there. And inside R0, I have 1. Inside R1, I have 5. Now let's look at the stack pointer. Stack pointer is pointing to somewhere. That's the bottom of the stack memory. Okay? So when I do a push operation, the value of R0 will be written somewhere in the memory. In this location, in the memory. Okay? And the stack pointer will change, right? Will it? Yes, the stack pointer changed because the position of the stack pointer changed. It changed by 4 cells. Why? Well, we'll get there when we learn memory because actually stack pointer jumps as 4 bytes and 4 bytes. There's a reason for that. When you learn memory, we'll get there. But the thing is, the last value I pushed to the stack was 1, right? So if I pop that value out to R2, I'm guessing that the value of R2 will also be 1. Will it? Let's go and check and let's press F10 and the value of R2 becomes 1. So that's how you do it. So that's how you check it. Actually, there's a way to look at that part of the memory and do the exact test we did with the memory bank representation, and we will do it, but after we learn memory. So my homework to you is, my advice to you is, go do these operations. Check R0 to R5, R1, R1, R5, and see if it really works. Check the values inside R5, R2, pop values out, and see if it really works. For example, R2, R3. Check these. Okay, this is my homework to you. Okay, any questions? No.